Okay, thanks very much to give the invitation to give this talk here. And I regret that I couldn't. It wasn't possible for me to come to India as already which I had planned actually to do. So it's okay. Maybe I just start with the first page. So the polaron is a well-known object in quantum physics, statistical quantum physics. So I'm just citing the statement from a paper by Spohn a long time back. So namely that it describes an electron coupled to a polar system, to a polar crystal. So and then the electron moves through this polar crystal, and then it creates a cloud of polarized nodes in the crystal, and this is changing the effective mass. This is changing the mass of the electron, and it's one of the main objects is that it's effective mass, so which is observed by an outside observer. So there's a quantum mechanic formulation. Don't ask me about the details of this quantum mechanic description, which I on which I'm not so familiar. So just you see on the bottom, you see this expression of the Hamiltonian, which is acting on a L2 space and tensor product with a Fock space. So now, fortunately for probabilists, so already Feynman in '66 found a path integral representation. Maybe I should add that it's actually in statistical physics and in people from quantum mechanics, there are many types of polarons, and it's actually a relatively well-studied topic here. So what I'm talking about is a special case, which is quite important, obviously. So which is this Fröhlich polaron, and for me as probabilist, okay, the important point is that there is a probabilistic formulation which goes back to Feynman. So for other type of polarons, such a path integral formulation is not possible. But here one starts with a Brownian motion. So that goes back to Feynman. So Brownian motion on three-dimensional Euclidean space. So and then there's a coupling parameter alpha, which is governing the coupling strength between the electron and the lattice. And then one defines a path measure. So which is okay. You start here with just a path measure of Brownian motion. And then there is, okay, in this Hamiltonian formulation, there is an interaction part, which makes the path measure self-attracting. And then, of course, there's a normalization constant. And then this is this polaron path measure. So you see the crucial thing is here, first you have a coupling parameter, and it's coming with a plus sign here, so in the exponent, which means that the path measures favors paths which are where the Brownian paths, so these paths are close together. On the same time, it's in a very short range in time, because you have an exponential decay if the time differences are large here. So this is this path measure. That's okay. That's well known. That is well defined. So you have this singularity, which causes a lot of technical problems, but it's a well defined object. That's not difficult to see. And then, okay, the physical quantities you are interested in are particularly this effective mass. So first, the ground state energy is the usual, okay, which you could also call the free energy. So it's 1 divided by n of log of the partition function. And then the effective mass, which is of basic interest in physics, is given in terms of can be given in terms of say the variance of the endpoint under this path measure. Now you see, okay, it's relatively plausible that for finite alpha here the path measure should still be in a sense diffusive. So namely that the variance of the endpoint is still of order t. This has become there are a lot of technical difficulties to prove that. But there is okay. because of this singularity. But you see, because it's essentially short range in time, you would expect that this limit exists and is finite here. So, and what turns out is that gives the inverse of the effective mass. So you would also expect that if alpha gets large, okay, that this variance, because then the interaction is stronger, then the variance gets smaller, and then the effective mass gets large. So now of particular interest is what is happening for large alpha. That's the problem of the effective mass in the strong coupling limit here. Now you can for the way I'm talking about it, so it's important that you can do a simple rescaling. You are just doing the Brownian rescaling of the path measure. So you're just rescaling the path measure by essentially replacing the time which are here by a lambda times t, where lambda is the inverse square of this effective mass. And if you are doing the simple computation, what you are getting is that for this Brownian transform path measure, so under this Polaron path measure has the following representation. Okay, you also rescaling time, so time is scaled with the original time times alpha square, and then you're having this double integral from 0 to tau, and then you're having this lambda parameter, which is what I would call the Katz parameter, which is the inverse square of the original coupling parameter. So you're getting this object. That's of course a simple computation you can do, and then you of course you have the corresponding normalization, which I call now the Katz normalization here. You see now this has a character of, you see what is happening if alpha gets large, lambda gets small here. And then you're having a kind of Katz model. So now this is in time parameters. So you see if lambda gets small, it gets longer and longer range in time. But on the other hand, you're having a prefactor lambda. So this you're then faced with this object here. So now. There was a famous conjecture originally, this Picard connection, which was proved in 20 years ago, essentially by Donsker and Varadan in a celebrated paper. Now, which is addressing this ground state energy, so the free energy. In other words, so you're looking at the time in this new time, so going to infinity, and then you let lambda go to 0, which corresponds to alpha, the coupling parameter of the original model, go to 0. Now you see, if you are looking, it's relatively plausible what comes out, but it was quite an achievement to prove that. You see, if lambda goes to 0, you have the feeling that it's getting more and more mean field type. So namely that you are averaging over the whole time. Of course, for finite lambda, it's always finite. Essentially, you have exponential decay, but it's essentially finite range in time. But if lambda goes to 0, you would expect that you're ending up in a mean field type model. So which would then look like that. So you're just averaging over the complete time interval here of the interaction. Now that is an object which is well known in large deviation, and you have the problems that they are on a non-compact state space, but that can be handled. So it comes out what you expect, that you are getting can be represented as in a variational formula, which is a supremum of this shock. This goes back to Elliott-Leibs. We called it the Shockar variational formula. So the shock of psi is just then given. That's an expression you would get from Brownian motion large deviation for the empirical measure of Brownian motion. So you're getting this variational formula. Now this variational formula is not totally harmless. So actually, but there was also a famous result by Elliott-Leibs. So going back to 1977, namely that this variational formula has a unique maximizer. So up to, of course, what is true is that every shift of a function, if a shift of a maximizer is also a maximizer of this, okay, it's invariant under shifts. So modulo the shift degeneracy, you have a unique maximizer. So what you can rephrase it in the following way. You have a unique rotationally symmetric solution, which is what is Elliott-Lee proved, and it's actually decaying exponentially fast, and any other solution is a shift of that here. So you have a whole family, a whole continuity of solutions of this variation problem, which comes out just from shifts of this rotationally symmetric solution here. So now a more complicated thing is this effective mass here, and then there is a celebrated conjecture. I think it's particularly celebrated because Feynman came up with it, and okay, there was further development in the physics literature. And only very recently there was a lot of progress on that. That's Richard Feynman added in his book on statistical mechanics, namely that the effective mass goes with the false power of the coupling parameter. You should remember, so the coupling, I'm always having these two parameters tied together. So I have this CUTS parameter, which goes to 0 and which is alpha to -2. So this effective mass. So if you are expressing in terms of this lambda parameter, it's going with lambda -2. So and the remarkable thing is that you even have an explicit representation of the constants in front of this. That's the prediction here. So that's a conjecture that's still not proved. So that you have this. This is okay. There are also some people also express doubts that it is correct in this form here. But anyway, that was the conjecture here. That you have an explicit expression in terms of this solution of the Shokar variational formula, the false power of this integral. Now there was very recently, essentially nothing was known up to 2-3 years ago. So I think the first rigorous result was actually okay. So something which was quite astonishing that it took so long time to prove it, but it's really a very difficult was a very difficult proof that was proved by Lieb and Zeilinger that the effective mass is actually going to infinity here. So now the first concrete lower bound was proved by Betz and Poser. So that I think the preprint was 1 year earlier. So that's I guess that will be published soon. So is the lower bound which goes with alpha to the power 2/5. So which is of course very far away from alpha to the power 4. Then there is a very recent paper 2 months ago, which was in the archive, namely an upper bound, namely that it can be go at most like a constant times alpha to the power 4. That's by Brooks and Zeilinger. And then just 1 week ago, I haven't time to read it carefully, is a paper by Mark Selke, which is on the, okay, it was on the archive 1 week ago, which gives a lower bound, which is of the order alpha to the power 4 times log alpha to the power 6. So it's still not getting that. So Betz and Poser used this representation by Mukherjee and Varadan, which is a very clever representation, representing okay the path measure and particularly also the variance in terms of a Boltzmann test process. But Selke is actually not using that. Instead, Selke is using cleverly the Gaussian correlation inequalities, which were proved by Royan, which was a conjecture for a long time. So that's that is heavily entering in that. I don't think that the method. Okay, it's just 1 week ago that I have seen. Okay, just 2 days ago that I have seen the paper. So my feeling is that it would not be able to the method would not be able to determine the constant or prove or disprove this conjecture here. So now, okay, how does this alpha up to the power 4 behavior appear? So okay, which means that okay, in terms of this lambda parameter, that if you're looking at tau minus 1 times the variance of the endpoint after doing these cuts, rescaling goes like lambda square if lambda goes to 0 here. So now you see, for the one thing which was also actually took quite some time to prove, so is that for a fixed parameter, the interaction is essentially short range in time, and you expect the center limit theorem that was proved by Mukherjee and Varadan, and also by Bates and Foser. So in papers which appeared just last year, namely that you have a center limit theorem with a variance parameter sigma square L lambda. Now this was okay, based on the representation by Mukherjee and Varadan, who express the thing in terms of Bose and test process, and in a sense they have an explicit, okay, a kind of explicit representation of this variant parameter here. So, but which is very difficult to analyze here. So now, for the claim that the variance here parameter goes like lambda square, and even giving the constant, there is an old heuristic argument of Herbert-Spohn here, which was in the paper of 80, which I cited at the beginning of the talk here. Now, okay, I'm just okay. It's just a one or two page argument, but at the beginning when I saw it, I thought it could not be correct. So but later I changed my mind about it. So you see, on time slots which are of length lambda to the power minus 1, because you remember. So maybe I go back to how it looks like. So on time slots which are based, which maybe are a little bit shorter than 1 divided by lambda, by lambda, you're having more or less a mean field interaction term here. So then Spohn argues that on time slots which are of order lambda minus 1, or actually he takes it a bit smaller for the argument. It's better to take it a bit smaller. The interaction is essentially of mean field time now. Now, you consider now the Brownian motion is only a mean field interaction. You can also look at the path measure where you only have a mean field interaction. You would have just this mean field model where we are just averaging out here the interaction over the whole time slot here, and look at this object. That's also, of course, with respect to the Brownian motion path measure. And you look what is happening in the time to infinity limit. Now, actually, what turns out is that it's just a shift it's possible shift of what people call Picard processes, which means that this is a Brownian motion where you have as a drift parameter, okay, the diffusion parameter is that of Brownian motion, and the drift parameter is just the gradient it's just a logarithmic derivative of one of these solutions of the Shokar variational formula. Now, which has I have told you that okay, these are all okay. If you center it at 0, it's rotationally symmetric, and that's exponential distribution, exponentially decaying tails, and you can possibly just look at shifts. So, but this Picard process, okay, if you're looking at the Brownian motion, which is drift given by this logarithmic derivative, it has a stationary distribution, which is just a square of this solution of the Picard of this Shokar variational formula. Okay, that's in a paper I had with Wolfgang König and Shiranjit Mukherjee, and then Mukherjee and Varadan actually proved something about this. Our model on which we are really interested in, namely that if lambda goes to 0, this CATS model converges locally. If you're looking at it on a finite time scale, it converges locally to the increments of this Picard process here. So okay, this development, particularly this Mukherjee-Varadan paper, okay, suggests that it is not totally wrong how Spohn argued that on small time scale the process should look like a Picard process here. Now, what then Spohn does is that he's chopping the time axis into intervals of lengths lambda up to minus kappa, where kappa is slightly smaller than 1. You could think, okay, I'm taking kappa equal to 1, but technically it's better to take it a little bit smaller here. Now, on such, now I have a picture here. On such, of course, I cannot draw r to the power 3, so that should represent r to the power 3. So what you are seeing is that if you observe the process, you are arguing that on time slots of length 1 divided by lambda, it should look like a Picard process with a kind of a random centering here. Okay, it's a little bit artificially drawn. So you look, it's of course a question how you define this centering. But okay, it's just a heuristic argument, and then you believe that on time slots of length 1 divided by lambda, you should have these random centerings, but otherwise it should here look like a PK process, meaning an ergodic, Brownian motion transformed by this solution of the Shokar variational formula, which turns it into an ergodic process whose stationary distribution is given by this psi theta square here. So now, if you look a little bit closer at it, and you are arguing now, you want to see how this centering should move, then you see that actually, if you're just looking at it, that's a simple observation that this centering should, okay, it's still the question how you define them, the centerings. You have to be careful with that. But if you do it properly, you see that the centering should still be tied together relatively closely. You shouldn't expect that on one time slot of 1 divided by lambda, you are at the point, and then macroscopically move away at another time slot. They are still coupled together very strongly, and that's actually the simple computation you can do essentially on the back of an envelope. So Spohn did his computation, and he looked at how he assumes that he can just replace the process, the empirical distribution of the process on these intervals by this Shokar maximizers of the Shokar variation problem, and then he just plugs that in, and he just says on an interval, on the ith interval, I'm having a centering theta k, and then he is expanding, assuming that he replaces the process empirical distribution of the process by just this density. He expands the interaction up to quadratic order. So if lambda goes to 0, and you get the Gaussian theory, and then you're getting the Spohn value of the effective mass, and you can, it's just the back of an envelope computation. Then you're getting the full conjecture here. So namely that we are having this behavior here, including the value of the constant here. So now, at first sight, this looks too simple to be correct. So that was at least my feeling. So now, evident problems is you see, can the empirical distribution reasonably replaced by just the stationary distribution, so the density of the stationary distributions. And then the other point is the PK in this argument, the PK pieces are put together as if they would be independent, except for the expanded interaction, and that's also, of course, that's of course not strictly speaking not correct, cannot be correct here. So. And then the next point is for the process on an interval to be a correct PK, you need actually the interval. So if you just do it on the interval itself, it's also not correct. But you need the interaction on the whole time scale. Now, why should you expect that you can so more or less separate out the theta movement completely from the fact that you actually need the interaction on the full time scale? So you see that is. You see this heuristic argument. Okay, it's really questionable if it looks plausible at first sight. Yes. Now we don't have an answer, so we have no. I should mention also. You see I'm talking here about the joint paper with Amir Dembo. So the main aim is to get a better understanding of the Spohr argument. I think in physics community, it's still taken more or less for granted that the conjecture is correct. But still get the mathematical understanding of this argument here, which we cannot do in the Brownian case, but which we can do in a simpler case, which I will explain in a moment here. If you look at the recent progress which have been made, on this conjecture, it's bypassing completely this heuristic argument by Herbert-Spohn, and actually, my feeling is the argument is interesting by itself. There might be other models where it is of interest here. What we looked at is at a simpler model, much simpler model, which avoids, for instance, all the problems with singularity and of the non-compact state space. It's the spherical Katz-Curie-Weiss model here, which has a Hamiltonian, which is given by with the same structure we had before. So it's a Hamiltonian with I'm writing here a minus to be in agreement with the physicists here. So in the exponent it comes then with a plus here. So now I'm having a symmetric density. In principle, you can take an exponential function, so as in the Polaran problem, but you can just also take a symmetric density, to make it simpler. Also, you can assume compact support, for instance, of this symmetric density, and then you have this Katz interaction, and then you have just spin variables which are on the D minus, which are on the sphere, but it should be at least a two-dimensional sphere, at least a one-dimensional sphere. So it should not be, you see, for D equal 1, it's just a standard Curie-Weiss. If you're looking then at the mean field model here, which I will explain in a second. It's just for D equals 1, it would be the Curie-Weiss model here. So just the usual Curie-Weiss model, but we have a spherical version of it because we need for the whole argument will rest on the fact that you have a symmetry, so a continuous symmetry here. So of course in the standard Curie-Weiss model you have a discrete symmetry which makes the situation completely different here. So now, you have to take a prior distribution of the sigma i's, which are just, of course, we just take uniformly distributed. So the first paper on this object was by Buta and Pico, which gave some estimates of the correlations lengths, which are actually not the predicted ones. So for the final answer. Now, as in the Polaran case, one has to understand the spherical mean field Curie-Weiss model here. So we replace this interaction here, which is essentially short range in time, by just averaging over the whole time scale here. So where you're getting the, now this is just the standard Curie-Weiss model, but then on the sphere here. So where you have this interaction here. So this Hamiltonian. Now, this had been analyzed in a paper by Kirkpatrick at Navas, which appeared a couple of years ago. To really get all the analytic results in this model is quite cumbersome and complicated, but this work had been done in this paper here. So if you look at the free energy, which corresponds to in the Polaran problem to the old result by Donsker and Varadan. So you're getting a variational formula, which is just the variational formula which comes out from from large deviations, which in our case would then just be the Sarnoff theorem. So we are having this representation of 1 divided by n log of the partition function in the limit. And but in Kirkpatrick and Navas, it's analyzed completely. So there is a critical value, which is twice the dimension here, and the set of maximizers is the following. So like in the Curie-Weiss model for which are on ±1 spin, you're having that for small temperature parameter, the maximizer of the variation problem is just the original the original measure on the spin variables here. So if you're looking at the maximizer, the mu's which are maximizing this variational formula, but if beta is bigger than 2D, then you're having a full continuous, like in the Polaron case, a full continuous family of maximizers, which are parameterized here by the sphere. And the mu theta is uniquely determined by beta, and the mu theta is uniquely determined by the temperature parameter. And the mean, so you see, like in the standard Curie-Weiss case, you are getting a tilt in the mean, but you have a whole family of these tilts depending on this parameter theta. But you are having a fixed radius, which is smaller than 1 here, on which this mean lives, and then it goes in direction to theta here. So. Now, as expected for the Polaron on time slots of order lambda -1, the sigma I should be distributed like a mean field case. Now, in the mean field case, of course, they would be distributed like IID with law, which are given by this mu theta, where you have this parameter theta. Now, for neighbor intervals of length lambda -1, the attached theta parameters are still strongly coupled together. The situation is really very, completely the same as what is expected in the Polaron case, and they would relax only after you take lambda -1 blocks here. So what you are looking at, so if you put it precisely, what you are looking at is you're looking at, say, taking means on essentially, again, you are subdividing the time scale into, which is in our case here discrete, into intervals of length lambda -1, and then you are taking corresponding block averages, and then you expect that the sigma case, so they should be close to the expectation of this mu theta for some theta. But if you're looking at neighboring blocks, they are still that should go away probably. So but if you do the computation, they should still be tied together very closely. So in order to see something, you should still speed up times with the parameter lambda -1. You see, you have lambda -1 appears twice. So you're first taking lambda -1 in order to take these block averages. And afterwards, you still have to speed up with lambda -1. This corresponds to this lambda square behavior. So, and then this y lambda should as lambda going to 0, converge to Brownian motion on the sphere, which is given on the corresponding radius. On the next slide, I have a picture to make it a little bit better visible here. Now, for a general function f, this is not yet proved, unfortunately, except actually in the case on the circle, which was a PhD thesis by Markus Petermann in Zurich here. So, but it's really for d = 2, it's using very special methods here. So to get that. Now here is the picture. You see the original sigma i's are jumping around on the sphere. So which is in my case just a circle. So you cannot expect that they are tied together. So this corresponds in the Polaron case that the Brownian motion, if you're looking very locally, it's still jumping around on time slots of length 1 of order 1. So you don't have so the original sigma i's are still on the original sphere, and they are jumping around. But they should, if you're looking at averages on intervals of length lambda -1, you are getting at these average points, and then they start to get close together. First of all, they are close to, in the limit, they should live on this sphere, but they are still tied together very closely. So you see, if you're looking to go into the next interval, the original points are still jumping around at order 1 on the sphere. But the average, say, if you're looking, for instance, at the next interval, should be close. You see that from the interaction. If you do the computation, are still tied together very closely. That in order to see something probabilistically happening on this smaller sphere with this average, you have to speed up time. So essentially, you look at there's a okay, it's wrong. It's lambda -1, not lambda here. So you have to speed up time, and then you should see the Brownian motion on the sphere. That's the picture here. So. Now, what is developed in a joint paper with Amir Dembo is a further simplification, namely, okay, we do an additional blocking. Essentially, we are replacing f by a blocked function, so which is constant over finitely many intervals here. Well, what we are looking at, we are expressing the interaction directly in terms of this average, so on these blocked averages we are taking here. And then we have this parameter m. So m you should think is lambda -1. So if lambda gets small, m gets large here. So you see, and then we are looking at the blocked average. So where we have finitely many betas in order to mimic the situation of the situation we have before, and we are just taking some over finitely many of these betas. Of these inner products, we are having this Hamiltonian here. Now, in order to, that's a situation which comes out from these results by Kirkpatrick and Navas here. Where you have this distinction if beta is small or large, so meaning the critical value is 2D. So that's the same here. So we should take the beta. The sum over the betas between bigger than 2D, because otherwise nothing of interest, may still be of interest. But for the picture we have in mind, nothing of interest is happening if this is smaller or equal to 2D. Now, you see, in principle, the true cuts case you can obtain by a formal limit. So we are taking, you could take, if, in the original case, we had this cuts parameter lambda, then we should take m proportional to lambda -1, and maybe take some small parameter epsilon, and then we would define this beta k we have here, depending on epsilon, in this way here, coming out of where f, for instance, is maybe if f is finite range, you would have for finite epsilon finitely many of these parameters. If f would be exponentially decaying, then you would have infinitely many, but decaying for fixed epsilon, the decaying beta k, which are decaying if k goes to infinity. And then you could first apply m to infinity, and then finally and in the end epsilon to 0, and then you should get the picture for say a continuous function f. And you should get the result I have indicated before here. But for the moment we have it only for this blocked model here. So namely that if you are speeding up, then time again of this taking these averages, this converges to Brownian motion. So you are getting this picture here on this sphere. So with an explicitly computable variance parameter, and the variance parameter, actually you can do the computation and compare it with the Spohn picture, and actually it totally agrees with the argument given by Spohn. So the variance parameter is exactly what should come out from the Spohn argument here. I guess I still have maybe 5 minutes, or what is the situation? Is that correct?
A bit more. You have maybe 10 to 15 minutes.
Okay. Maybe I still want to. It had turned out actually even for this for this result in this simplified block situation, there was still some difficulty to prove it here. So what we needed actually was that was a point where in the end it opened the way to do it, namely that what we did was an a priori. So I will mention towards the end why this was very important for us, at least, to have this a priori bound, so which we were doing by bare hand, namely to prove that if you're looking at these blocked averages, which I can write in terms of, okay, you have a radius, and then you have this theta, which is on the sphere. So you see these blocked averages, if I'm going back to the pictures. These blocked averages should be close to this radius, but then still, okay, you don't know where they are. So that's, of course, you have all the possibility on the sphere. Namely, what if I write it in this form here, then what we prove is that with a probability which is okay, okay, close to 1, up to say maybe stretched exponential behavior, that you have this radius which is close to the radius which comes from the variation formula up to essentially m to -1, and then you should add some delta. And then also neighboring points are also close together up to m -1 plus delta. Yes. So you have this situation here. So now this we did just by bare hands. I have to say that probably, of course, it's not totally clear that you need something like that, but in the way we did it, it was actually very important to have this a priori bound. And that is probably something which, at least in the way we did it, would be a little bit delicate, okay, maybe even more delicate in the true cuts case. So for that reason, it was actually nice if you could do without that, because my feeling is for the true cuts case, and then even if you're more ambitious for the Polaron case, to prove something like that should not be totally, it's probably not totally easy. So now the next step is to do essentially a little bit more sophisticated, but looking at what Spohn did. So you see Spohn did in his case, he just said, okay, I'm having in the limit the Gaussian model, and he computed the variance for this theta parameters for this Gaussian model. So that you can do here, and it's a simple computation what this Gaussian model would be here. So you're looking first, because in the end we expect that this difference you see if you have this a priori bound in the essentially you think that essentially you should get m -1 here and also m -1 here. So I scale that up with square root of n, and then I'm looking at the difference of this radius with the radius which come out from the variation formula. Okay, I have yeah. Okay, I'm cheating here a little bit. So in principle, you see in the limit you are getting just this rho beta. So there's no m involved for this rho parameter. But what we do, it's actually, it turns out to be better that we still do, even for in the variational formula which pops up coming up from the Sarnoff theorem, that you plug in this parameter m. So this rho of beta is in a controllable way can compute it out, and it is close to the true parameter. But it's actually better to take essentially the correct centering depending on the parameter m, which in the limit goes to the correct thing here. So you see these objects are random, but this constant rho m of beta, I'm not writing out it here. I have not written out what it is. But this is just deterministic, and this converges in a controllable way to rho of beta here. So. And then you are looking at the differences of neighboring blocks of this angle parameters. Also, scale it up at the end. And for that, for formally to do the limit, you are getting a Gaussian model here. So a little bit formally written, you have it given as as a Gaussian interaction, but it's on the Euclidean space here. So because you are scaling up, you see originally the theta are on a sphere, but because you are scaling up, of course, essentially you are expanding in the tangent space. So because you are these points are together quite closely, and you scale them up, and then I regard them as elements in the Euclidean space. So of course, for the Gaussian model, you have a model in the Euclidean space. And okay, you can and this interaction is just a quadratic function. You see the x are living on r to the power n, so which depends on the number of blocks you are having, and actually it's just if p was okay, probably don't remember, but p was the number of betas I have, so the dimension is just d times the number of parameters we have. So you see, if for the true model, in principle, you would have, for the true cuts model, you would have an infinite dimensional version of that here. But so you have this Gaussian model. And then that you can do Perron-Frobenius. Now you see Perron-Frobenius type things are difficult on non-compact state space here. So, but because you are in the Gaussian situation, you can explicitly by linear algebra, you can compute the Perron-Frobenius eigenfunctions. And then you can represent the Gibbs distribution if you look at then in infinite. On the infinite time axis, you can write it as through a Gaussian transition densities here. So now, if you look at the variance which you are getting out from this Gaussian transition densities, then you should get the correct correct variance parameter for our Brownian motion. So you see, this part is essentially okay. The part which just Spohn took for granted that it works in this way here, and then out from this Gaussian computation you are getting the variance parameter here. So now for the convergence to Brownian motion, the approximation actually which was done in step one is then of course not good enough, and you have to do something a little bit more sophisticated. And then there was a step actually where I have to admit that I don't know if you have done it in the optimal way here. So namely, what we would try to do is for the correct, you see, for the correct interaction we are having, which depends on n, we would like to do a Perron-Frobenius type argument and prove that it converges to the Gaussian model. In the end, we do that, but we found it difficult to apply results from the literature on Perron-Frobenius. But actually, I'm also not a specialist on this topic, so we had difficulty to find a result in the literature which was just doing this the jobs. So the problem is, you see, you can easily construct example where say even very simple things on but where on non-compact state space Perron-Frobenius more or less collapses completely here. So now the point is that for the Gaussian model, we can do the Perron-Frobenius on the full Euclidean sphere just by bare hand, by just more or less linear algebra computation. Now we want to do a kind of approximation step, and what we did was just the following. You see, the point is that you see for finite m, for the true model, of course, you are on a compact state space because you are still on the sphere. But in principle, you see you are scaling up with growing m. You are scaling up everything on the tangent, more or less on the tangent space. And so if m goes to infinity, you are ending up in this non-compact situation here. So now the way we did it was just we took this object here, so which is a true object, and we just took the Gaussian eigenfunctions we had and transformed it to that here. Now this is of course this doesn't work because it's the Gaussian. You see, this doesn't give you a Markov transition kernel here, so because you are just taking the eigenfunction from the Gaussian case. but it's actually close to the Markov transition. And close, you have to be precise what you mean by close. So close, first of all, you need heavily the step one in order to, you see that you have this a priori bounds, so which we proved. Namely that you are not very far away from the square root of n behavior. But of course, it's also not a transition probability, but it's close to a transition probability. And then there's a perturbative way to improve it, to improve the eigenfunction, which is just done by bare hand, to improve the eigenfunction in a perturbative way, in a controllable way, in order to get the Markov transition, to get the correct pair of Frobenius. Now this is not quite correct. So we just did an approximation procedure which we had to apply twice. So in order to get an object with which we can work here. So now what we prove is that for large M there are transition densities on the Euclidean space, such that the Markov chain is in total variation close to the M Gibbs distribution. So we are not getting fully the pair of Frobenius for this object, but we are getting an approximation of that, where we can prove that in total variation it's close to the Gibbs distribution on time intervals of length m squared here. So for that reason we had to do the approximation twice, because in the first step we only get it on time intervals of length m, or slightly smaller, but if you do it another time, then we get it on m squared. If we would have done it, the iteration procedure more, then we could get it to the m to the power 3, 4, etc. Yeah, but we also know that the transition kernel is still close to the Gaussian transition kernels. Now that we control less precisely than the approximation of say approximation by the true model by this Markovian chain, but we know that it is still the one-step transition kernel is still close to the Gaussian transition kernel up to a factor which, as m goes to infinity, is close to 1 here. Now then we can use the central limit theorem for the Markov chain to Pm, and then we can read off the variance from the Gaussian model here. So then that is, you see, in this case it's just the crucial point which is still missing in a way in the true Polaron model here. So now then there is still there's still the problem. You see in the end, essentially we do everything on a tangent space. So technically we are just do our movement on the sphere by rolling it on a tangent plane. Yes, so in order to get something which we can do in a Euclidean space, which we need in order to do this Gaussian, to do this approximation by the Gaussian model, but then we have to turn it back to a Brownian motion. Of course, in the end, we want to have proof that it is Brownian motion on the sphere. But fortunately, there's a very old result by Jorgensen, which is proving the central limit theorem of this random walks on spheres to a Brownian motion on the spheres, and we can use that and prove that we can turn that back to a Brownian motion on the sphere. So yeah, okay. To me, it looks that if you do it on the non-block case, it could be that the most cumbersome part would probably be to do this a priori bound, which in that case I would have a little bit we have started to look at it, but we don't know how to do it. And of course, the even more challenging thing is if I could do this kind of argument for the true Polaron. So now, of course, the situation has changed a little bit since a couple of days, I have to say. but because it's for the first time, okay, I haven't checked I haven't read the paper, but it looks like that there is now for the true Polaron, it's a rigorous bound which gives the alpha to the power 4 behavior up to a logarithmic factor, which is of course great. But it looks that the method could never give of course that's a great result. But it looks like that the method could never really tie to this variational problem, which underlies the prediction for this alpha to the 4 behavior, including the correct constants in front. So to go back to this. And it looks like probably the methods could not catch this constants correctly, which really comes out from this Plon picture, which we are trying to mimic in our simplified model here. So, okay, that's the situation here at the moment, I guess, for these problems around this Polaron problem and this very celebrated conjecture. I guess it's very celebrated also because Feynman originally came up with it. So actually, Herbert Spohl once told me physically this strong coupling limit is actually not so relevant in the sense that in experiments they cannot go with alpha to very large values. Okay, that's all I have to say about this situation. Okay, thank you for your attention.